You see, the periodic table is so much more than just a boring list of elements. It's really a map. It's a secret code. You could even call it the ultimate cheat sheet for chemistry. Its structure isn't random at all. It's this brilliant system that reveals the hidden rules for, well, pretty much everything around us.
Okay, so if we're going to crack this code, we have to learn its language first. And that all starts with understanding the grid itself. The rows, the columns, and all the different neighborhoods where the elements live.
So let's start with the horizontal rows. We call those periods. The easiest way to think about them is like floors in a building. As you move down the table from period 1 to period 2, you're just adding another floor. Or in chemistry terms, another shell where electrons can hang out. So an element down in period 4? Yep, it's got 4 of these shells. Simple, right?
Now for the vertical columns, which we call groups, if the periods are the floors of a building, then the groups are like families living in apartments stacked right on top of each other. And just like a family, everybody in the same group shares similar traits and behaves in similar ways. And that's all because they have the exact same number of electrons in their outermost shell. And that brings us to the next level of organization, the element neighborhoods, or blocks. Way over on the far left, you've got the S block. That's home to some seriously reactive metals. Then, on the right, you've got the P block, which is a really diverse area. It has everything from gases like oxygen to solids like carbon. And smack dab in the middle, that's the D block. And that's where you'll find familiar metals like iron, copper, and gold. So, now that we've got the lay of the land, let's actually meet some of the residents. We're going to get to know the major element families and find out what really makes them tick. The biggest divide on the whole table is between metals and nonmetals. Metals, they pretty much own the left side. They're usually shiny, you can hammer them into different shapes, and they're great at conducting heat and electricity. From a chemical point of view, their main goal in life is to get rid of electrons. Nonmetals, over on the right, are basically the polar opposite. They're often dull, they're brittle if they're solid, and they are terrible conductors. Their life's mission? To grab electrons. And this is where you really start to see those family resemblances we talked about. Take the alkali metals in group 1. They are all incredibly soft and ridiculously reactive. Their next-door neighbors in group 2, the alkaline earth metals, are pretty similar, just a little bit harder and maybe a notch less reactive. Then you go all the way to the other side of the table, and you find the noble gases. They're all gases, and they have absolutely zero interest in reacting with anything. So, why are those noble gases so standoffish? What's their secret? Well, it all comes down to their electrons. They have a completely full outer shell, which is basically the most stable an atom can possibly be. They've already reached chemical perfection, so they have no reason to mess around with other, less stable elements. They're the cool, aloof kids of the periodic table.
And that right there brings us to the real aha moment of all this. The true genius of the table isn't just in how it organizes elements, but in how it reveals these repeating, totally predictable patterns in their properties. This is where we unlock the periodic law.
This phrase. This is the fundamental rule of our entire cheat sheet. The periodic law is the key that cracks the code. It just means that when you line up the elements by their atomic number, 1, 2, 3, and so on, their properties start to repeat in a predictable cycle. This is what turns the table from a list into a predictive powerhouse.
So let's look at the first huge trend, atomic size. Now, you'd probably think that as you go to the right, atoms would get bigger because their atomic number is going up. But, and this is wild, the opposite is true. As you move from left to right across a period, atoms actually get smaller. But as you move down a group, they do get bigger, just like you'd expect. So what on earth is going on here?
It's basically a cosmic tug of war. As you move to the right across a period, you keep adding more and more protons to the nucleus. This stronger positive charge pulls all the electrons in tighter, which actually shrinks the atom. But when you move down a group, you're not just adding protons, you're adding entire new electron shells, which are way farther out from the center, making the whole atom much bigger.
This tug of war also explains our next big trend, ionization energy. That's just the fancy way of saying how much energy it takes to steal an electron from an atom. Since atoms get smaller and that nucleus pull gets stronger as you go to the right, it takes a lot more energy to rip an electron away. And since atoms get bigger as you go down, those outer electrons are farther away and way easier to snatch. So ionization energy goes down. See the pattern?
So really, it all boils down to a balance of 3 main forces. First, you've got the nuclear charge, the protons, pulling the electrons in. Second, you've got the electron shells creating distance. And third, you've got something called the shielding effect. Just imagine the inner electrons forming a little crowd around the nucleus, kind of blocking its pole from reaching the outer electrons. These three forces are always competing, and that's what creates all the amazing trends we see.
But of course, chemistry just loves to keep us on our toes. These trends aren't perfect rules. Take this for example. You'd expect it to be harder to remove an electron from oxygen than from nitrogen, right? I mean, oxygen is farther to the right. But it's not. Turns out nitrogen has this super stable arrangement of its electrons. The universe loves stability, so it holds on to nitrogen's electrons even tighter than oxygen's. These little exceptions are honestly what makes chemistry so cool.
Okay, let's bring this all home. We've decoded the grid, we've met the families, we get the patterns. So what? Why does any of this matter? Well, it matters because it transforms the periodic table from a static chart on a wall into an absolutely incredible tool for prediction.
Here it is, the main takeaway. You do not need to memorize the properties of all 118 elements. By just knowing where an element lives on the table, you can make a really good guess about its size, its reactivity, and how it's going to behave. It is the ultimate scientific shortcut.
Today, we've got 118 confirmed elements filling out our table. But think about this. When Dmitry Mendeleev first came up with his version, he had the genius and the guts to leave empty spaces for elements that hadn't even been discovered. He predicted the existence and the properties of elements like gallium and germanium years before anyone ever found them, just based on the gaps in his chart. Now that is the power of this code.
So, if this elegant little map predicted elements before we even knew they were out there, what else is it telling us? As scientists push the boundaries, creating new, super heavy elements, what other patterns might show up? What could the very next discovery reveal about the fundamental rules that govern our entire universe?